Funk, and I'm one of, that's my picture down there in the lower right corner. I'm one of the solutions team managers here at Imaginet, and I've been with Imaginet. This is my 20th year with Imaginet, and it's which just absolutely blows my mind. I swear I'm not a day over 35, and when I look back, it's just absolutely shocking. So one of those things that I do in my role is these type of webcasts that we're doing right now, where we take different technology and kind of show it off to clients and talk through and kind of in some cases, figure this out together. It's been one of the most interesting things for me in the past 20 years is some technology comes along and it is immediately recognizable what we should do with it. And others come along and we kind of figure it out. And a lot of times it's this co-education where I am teaching people about the technology and I'm learning about what environments it could go into, what different applications it could be used for, is all of that. And that's kind of where Imaginet, that's a big part of what we do. I skip right past that one. So a big part of what we do is that type of thing with customers, where I mentioned that co-education. You know, we're learning together, and that mutual education, a lot of times we'll call a discovery, where we're going in and looking at what we have and talking to a client, saying, well, hey, this could work, or how are you doing this, or what if we applied that? Then we take that and we optimize it. And then we're able to enhance productivity through training and support, and so many times it's a virtuous cycle that leads right back around, and we're just doing all of that type of thing again. And that's a large component of what I do with Imaginet and my group, which is the professional services group with Imaginet. Now, I mentioned Imaginet. We're actually part of a larger company, RAND Worldwide. And Imaginet, we deal with we are a provider of Autodesk, ARSUS, Leica Geosystems, and a big thing is professional services and training. Professional services is really where I focus, right on the Autodesk side, whether it's implementations, consulting, training, those types of things. We do have some sister companies, RAND 3D, and RAND 3D is one of them. They're the provider of Dassault software and Dassault and PTC training. And then Ascent, and if you've taken a class with us, or pretty much any reseller, in the last 20 years, you've probably used Ascent books that are part of that, and that's written by one of the divisions of Imaginet, RAND, excuse me. It's our sister division to Imaginet. It's really great because we get to be involved with the creation of that material, talk to them, and make sure we're all leveraging it the way they expect us to, and that what our clients are looking for is included in it. So, and Cassie, Mark sent me a new slide, and I forgot to replace it. This is one of our older slides that we have. It's relatively up to date of all the locations. The big thing that I would tell you is that, you know, we're all across North America into Canada, and it's been we've got this real depth of knowledge on the technical team, and then this breadth of reach that we can do, where we can go out and we can, you know, a lot of times we're where you are in our offices, and we can work with you on those things. So I mentioned the idea of professional services and training. You know, these are some of the different things that we offer. I'm sure if you've been involved with one of our webcasts before, you've seen something very similar to this. A couple of things I'll just point out. The idea of data and product lifecycle management, implementations, consulting, that's what I deal with day to day on the manufacturing side. That's where our strength really is in so many of these things. What I think is cool is that we've specialized into different things, where we've got people specializing in BIM, CFD, the reality capture, and the facilities management. So all these different professional services are something that we would offer. And I mentioned we have the training as well. We can do that in a whole lot of different ways. So as you're looking at some of this, I'm going to be using some tools today with Inventor. I'm going to be using tools today with Fusion. There's a lot of different options out there, and if this is something you want to get formal training on, we do that in so many different ways, whether it's in-person, live online, custom classes, blended learning, productivity now. There's just so many ways that you can access that. So that's kind of a big, broad scope of Imaginet there in just about 4 or 5 minutes. But I want to move on, and I want to talk about what we're looking here today, this idea of generative design. And this is an interesting idea, and it's relatively new to me. I've been learning a lot about it, even in the last few years as it's come along, as different tools become available. And I thought it was so cool when I was getting ready for this webcast, I ran across this article. And this was in Tech News. I think it was Wired was the ones who had written the article. But it was all about this Volkswagen bus that they had made a purely electric vehicle. So this is Volkswagen had spent some time to take one of their old buses. It's, obviously brand new. It's, I think it's the Vanagon, if I'm not mistaken, not the microbus, but the Vanagon. And it has been manufactured to be an electric vehicle. And I think it's a prototype test. So just at a glance, this sure enough looks like a Volkswagen microbus. What's interesting is I'm going to pull out some of the details here, is Autodesk actually was a partner in some of this and used generative design to create a lot of the components that are in here. So if you get, some of these details, honestly, that rearview mirror looks to me like Spider-Man stuck it on there. It just looks like a web went out and attached to that. Same would be true of that support. That's one of the seats in the back, and that's a support that's underneath of it, and it does. It has just this kind of spider web look to it. This is part of what generative design can do. Obviously, in any vehicle, weight is a factor, but in electric vehicles, it becomes more of a factor because our battery efficiency hasn't quite reached the point where we have efficiency and long distance like we would have with an internal combustion engine, right? We've got to be able to manufacture these vehicles that are as light as possible. The battery's the heaviest part. It's great if everything else is light around that. And as you look at this, these are some really interesting designs. So it's both aesthetically interesting, but more importantly, it's as lightweight as it can be in context of this. So it's just a great example of how generative design is being applied for real. Because I've seen some of the designs I've seen come out, I'm like, well, that's really interesting, but would we actually use it? This, I just think, wow, what a great example of how that's really going to be used. So over the next about 35, 40 minutes here, we'll go through, talk about generative design and a few of those pieces, and I want to get into that. So I've got my green tea fully steeped right here in my right hand, so I should be all prepped and ready to go with that. So let's talk about conceptually what we're talking about with generative design, and it's really all about design exploration. The idea would be we can take a cloud power, cloud computing, some machine learning algorithms, and be able to generate hundreds to thousands of design options. And what it's doing is and these are CAD-ready solutions. We can have manufacturing constraints. We can have product performance requirements. It's not just going to come up with something completely unusable. Now, admittedly, out of 1,000 options, most of them are going to be just unusable, silly, ridiculous, unmanufacturable, or possibly manufacturable but a very high cost. So the beginning of this whole chain is that human element, someone going in, setting up the constraints, setting up the product performance requirements, understanding what this needs to happen, what the output needs to be when we're done, and then putting that through. So if we just take a step back and take a look, it's possible someone could come up with this design eventually that was both structurally sound, aesthetically pleasing, and it met the requirements that we'd need. The number of iterations that would have to go through may be very, very high. And that's why we're able to leverage this generative design to do that. And very typically, we do go through design iterations. I mean, absolutely. We come up with some concepts. There's a few dead ends. We take a few forward, and we pass them back and forth for evaluation. We say, well, yeah, I don't know about this. Then we kind of look at it. Once we say, yep, this is the concept that we're looking for, let's take that on. Let's look at manufacturability of this. We have a validation phase where maybe we test it a little bit with weight and stresses and try to understand what's going on. And then finally, we've got a product that we're going to have that's coming out of that. And to me, this bracket, this brace that I'm looking at here that's going to mount up to something, that's what I would see every day in industry, something along those lines. Well, the idea of iterative design is to take that and, now we've got so many different options. We've got this iteration phase that we can just do thousands of iterations through. And these can be validated, manufacturable options. Once we choose one of those, then we can move right into production off of that. So the iteration phase, we can front load that. It's going to take less time because we're leveraging not just a computer, but we're leveraging many computers through cloud computing to go pull all of this together. And then we pull something out of there, and that's what we're going to produce once we've got that decision made. So you can see in the background there's the original design style overlaid on top of that, and now we've got this one. We can reduce that design to production. Now, admittedly, there are times when I just want to bracket. If it's a little heavier or not, it's not going to matter that much. Great. But in instances such as aerospace, such as in design with cars, such as in plastics, all these different consumer products where we're looking to have something that's functional and light, this is just a fascinating way to begin extracting all of this. We can take this information, run it through those iterations, and then pull out the one that we want. Now, when we get into this, I want to point out a couple of things. And I am going to use Inventor with the Inventor shape generator. And that's not quite generative design. It uses some optimization tools. And this is a tool, if you're using Inventor Professional, it's in there. You have it today. I'll just kind of point it out to set up what that looks like. Generative design is going to go much further with that concept. And it's a explorative methodology required as opposed to an expert setting up the problem exactly the way that we want to go. With Inventor, with our topology, we're looking for light weighting. We want to take this and say, all right, this is 5 pounds. What can we strip away to make it 3 pounds? And it really comes out to one solution based on the accuracy of our confinement. We've said we're pinning it here. We've said we're locking it here. And how does that go? And that's typically not going to be manufacturing aware. That's something that we're generating, just like if I were to draw anything in Inventor, same case. We're just drawing it. It's there. It's not really manufacturing aware. Generative design is goal-driven, and you'll see that when we go through what I'm talking about. It's a very different way of approaching it. All viable outcomes are presented. We can go through and determine which ones we want, and we can do trade-offs for performance. Basically, we can say, well, let's not just make it as light, but we want it to be as stiff as it can be under these conditions. We can look at those types of things. And manufacturability is taken into account right along with that. And this is being used. Generative design is being used today. There was a case study from Autodesk. It was presented at Autodesk University last year. And the idea was with Airbus. Of course, here we're in an aerospace application. We've got to reduce the weight of things. They're looking to reduce the weight, particularly on commercial planes. If they can reduce the weight of the plane itself, that is more passengers, that is more luggage, whatever that they can take on. So they reduced the bulkhead weight, by 25 to 30 pounds. And they came up with a concept that I can tell you as a designer I never would have come up with. Maybe eventually I would have, but just looking at it, I'm like, wow, it's really interesting how they came up with this idea. And they were able to reduce the component count in that pretty dramatically. They also were able to reduce the cost of that because we've got fewer components. They go together in a simpler fashion. They're able to come together with this concept and idea that's part of that. So this is a real-world application of this type of design being used. So let's take a look at how we can use it ourselves. And the first one that I want to talk about is the shape generator within Inventor. Part of the reason I want to talk about this is I think this lays out the differences between the two pretty clearly, and it sets us up to I'll say it sets us up to win. It sets us up so that we can take this information. When you see the generative design idea, it kind of makes sense what generative design is and what the differences are. So here's the idea. We've got within Inventor, we would fully define the part. You would design the part as you intend for it to work. You go through, you set it up, you create it, and then we begin to say, okay, I want to see where we can remove information from this part. Not information. I want to remove material from this part. So what I want to do is give it specific information, specific requirements. What material do I want it made from? What constraints? What loads, symmetry, mass? What are the things I want to maintain about this? So we have the model fully created. We can open it in the shape generator environment. We apply constraints and loads. set up all the settings, and then we run a shape generator study. And a shape generator study takes into account a lot of different things, but at its core, it's really running an FEA study. It's kind of looking based off the information you've given me, how do I want to do this? So it creates the mesh, it's a tetrahedral mesh that it'll create through there, just like we would with FEA, so that we can gain an understanding of what we want this to look like, and how we want this to work. So the shape generator tool, we've got, well, the first thing you do that we're going to begin using this is actually create the model. So this is the complete model. It's got the overall volume and shape of the model. It's got all of the contact points. It's defined. And really, most likely usable. It's not that it's an unusable part. We just want to say, hey, we've got this thing fully defined as is. This is what I want to take and begin working with. I want to leverage the shape information in Inventor to go through and do that. We can go through and then assign a material, and we're going to assign some constraints to this model. So this should sound very familiar if you've dealt with FEA. This is the same idea. What material, what constraints are in place, including loads. I can assign what load I want applied to this model. So this is right down the line. This is just how we would set up an FEA model, constraints, material, loads. The one thing we're going to do a little bit differently than what we would typically do when using just straight FEA, we can determine shape generator settings, what our target mass is going to be, do we want to reduce the original, what's our target we're looking for. And typically we could reduce mass by 1%, we could reach a target mass, we could say something has a component has to be a certain size, or we could have a mesh resolution of X amount. There's certain settings we can put through there so that we can control. Again, I'll walk through this, so this is a lot of talking, but I wanted this to be clear. A key piece of this is we can preserve regions that we want to stay in place. And you can do this with a rectangle, you can do it with a cylinder, or box, not a rectangle. But what this does is it sets up areas of my model that stay the same. No matter what else happens, no matter how else you're going to evaluate this, this has to stay here. Once we've got the regions established, we can tell it whether it's symmetrical or not. Do we want, which is it symmetrical side to side, top to bottom? How do we want that to work? That way we're not going to get some strange shape that's really going to go out of the way and twist things or whatever. And then finally, we can run the analysis. Once we run the analysis, it gives us a mesh which we can use then as the basis for creating our model. The mesh doesn't change the model. This does not create or remove geometry from the model. It just goes through. So as a basic idea, we've got the original geometry. We analyze it to get a mesh. We take that mesh and send it up to the main model, and we use that idea to remove geometry. We use the mesh as a guideline. This is what we want it to look like when it remains, so we know what we can remove. So it's strange to think of this being a manual process, but this is a way that we can optimize the shapes within Inventor. When we take a look at the iterative design, it's a little bit different. But I am going to share my screen, and I'm going to pop up, I think I am, there we go, my Inventor. So here's that shape that I was just looking at, with all the information about it. And what I'm going to do is I'm going to come along and just walk through those things that we had just a moment ago. So here on my 3D Model tab, I do have Explore, and I can go to my shape generator. To me, it looks very, very much as though I'm working within an FEA analysis, right? If you look, I've got the same things going right across here that I can take a look at. What I'm going to do is come through and assign a material. This thing was already set up for steel. I'm good with that. We'll leave the material as steel. If I wanted to, I could overwrite it and apply a different material, and I could have multiple studies where I have that material. I'm going to go ahead and put in a pin constraint, and I'm just going to flip this thing around because I want pin constraints all across the bottom here. And this is just how this is being held. Very, very common when we're dealing with these types of shapes and everything. These are basically areas that I want to stay the same as I go through this. I'm also going to put in a magnitude. So I'm going to come in and put in a I'm going to put a moment as part of this, and I'll say we want a bearing. I'll go here, pull it off of this face. Yep, perfect. And I'll put a force associated to it. So I've got most of the things that I would need for a FEA study. I've got a material, I've got fixed locations, I've got a force. Most of the time, that's a big part of what we're looking at when we're saying an FEA study. Like so many things in Inventor, we work from the left over to the right, and I'm going to keep going, and I'm going to go with preserve region. And this is interesting. I'm defining an area here now that I want to keep. You can see as I drag this out how it kind of encompasses that. It doesn't matter if I make it bigger because there's no geometry. You know, if I make it too big, it doesn't matter too much. There's no geometry beyond there. So this is what I want to keep. No matter what else changes with my study, I want to make sure that information is there. I'm essentially keeping that part of it. And then I'll come down here to the bottom, and I want to keep these areas as well. So I'm just going to go ahead and preserve some regions down here. I want to keep this one. Make sure it's big enough. Sounds good. I want to keep that one. And I'll just walk down here and basically do the same thing when I keep that one. And that one. Now, since I'm picking cylinders, it's automatically adding these as cylinders. I could switch it to a box, which I'll use here in just a moment. But the idea is I'm defining the areas of this that I want to keep. So when we do run the analysis for understanding how this goes together, how these relate to each other, what pieces can we remove, it's not going to take those into consideration. It's preserving that geometry. It's going to keep it there. And I'll just extend this out this way and out this way, something like that. Okay, perfect. So I'll say, yep, that's the areas that I want to keep. I've got my region set up. I've got my general information set up. One last thing I'm going to do is I am going to go to my symmetry plane. And we're going to make sure that's symmetrical running right down the middle of that. Because the way it's set up, it's symmetrical on either side. Great. Now, if I go through here, I can determine what I want to run. What type of study am I running? In my case, I'm going to say I want a target mass of 2.99 pounds. That's fine, that's fine. I'll say okay. Sounds good. And so the mesh, it'll generate a mesh based off of this as it goes through, taking into account all the pieces that I have. I haven't quite got to generate shape yet, and it takes a little bit for it to do it. So I'm going to do the cooking show approach where I've got this already baked up, and we'll pull that out. But the idea would be is I would generate a shape right off of this, and it would take into account my FEA information of how it's fixed. It would take into account the areas I want to preserve. It would look at all of that and say, okay, based off of that, let's pull this across. I'm going to go ahead and grab this final version. And it generates for me a mesh based off of that. The mesh represents the regions I want to keep and all of the other information about that. So if I take a look, the shape generator went through and it generated essentially an FEA model plus the regions I want to keep so that I can see to maintain the size that I need. And you can see originally it was 4.51 pounds. It's now only 3 pounds. We reduced mass by 33% if we remove these areas. However, we're still within the safety factor that we need to be, and this mesh has been generated for that. Now, this doesn't remove any material. This doesn't change my part. This doesn't edit anything to this point. What I have to do is promote that shape, which I've already done here, up to the top level, and then I can use that shape to define some areas that I want to begin cutting out. So I'm probably not going to go follow along perfectly. I'm going to come pretty close and give it some sense of that, where I want to be. I'm actually going to turn off, if I turn off the mesh, you can see I've got some simple sketches in here, and I'm just going to extrude these. Take this right back over to here. I'm going to extrude these sketches just to remove some of that material. So while it gave me this kind of more organic looking shape, really commonly what I would want to do is come through and just take some standard Inventor features, and now I'm going to remove this. So we get a sense, and this is kind of what I was talking about, I don't want to, it's not a manual process. I mean, it's not something I'm cranking out by hand, but it did go through, generated this for me, and now it's up to me to make the changes to pull this out. But now we've got a block that is going to meet my criteria for strength, but it's really reduced how much it weighs overall. That is the goal. That is kind of the common feature of using the shape generator within Inventor. Now I want to move away from Inventor and into Fusion 360. So true generative design is the way you're going to access it is through the desktop connector and AnyCAD. And AnyCAD works both ways. We can take a file and bring it into Fusion 360. It has AnyCAD technology. It'll bring in Inventor. Basically, it links it in. And if the original Inventor file updates and change, it'll update and change in Fusion 360. And we can then take it from Fusion 360 into Inventor. And the desktop connector is the tool that sends that information back and forth. I'm going to come back to that. I'll show that in just a minute because I want to talk about how we're going to, let's take a look at this within Fusion, and then I'll talk about how we could leverage Inventor to send that over to Fusion. So I'm going to share my screen again. All right, so here I have my Inventor. I'm going to pull up my Fusion 360. And within here, I've got a part. Now, this was created within Fusion. And Fusion has, a lot of people, when you get in, they say, well, gosh, Fusion doesn't seem to have many tools in it. It seems really simple. There's actually a lot of things going on. They have a very clear interface, I'd say simplified interface that works with this. But generative design is one of my options that I have here. Now, if you'd recall, the way I started it with Inventor, and this part looks like I could have drawn it in Inventor. I actually probably would have even made it simpler in Inventor. But conceptually, it kind of looks like an Inventor part, right? I go through and, here's a base, here's a this, here's a that. And now we've got this particular component, generated from that, this little bracket generated from that. With generative design, we're going to do things a little bit differently. So if you've never used Fusion before, what I'm pulling up here is my data panel. This is how I go and access the different data that I have within here. And I'm going to go take a look at my GE bracket. So I wanted to pull this one up to show the different locations, right? This is kind of what this bracket appears to be as a general idea. But with generative design, I don't want to start with that shape, put a mesh on top of it, and then work backwards from that mesh. What I want to do with generative design is give locations that are preserved. Essentially, I'm going to say, I need these 4 holes. Then I'm going to give obstacle geometry. It's areas to avoid. And that is in red. So my green is things I'm keeping, and in red are the things that I'm not keeping, effectively, right? I want to avoid these areas. I have to leave something open here. So this has to be a hole. This has to be a hole of this size. This has to be a hole of this size. Then avoid an area this big, avoid an area this big. So what I would define here would be my preserved geometry, specific, could be contact points. It could be specific areas that I would want to keep, and then what I would want to preserve, or excuse me, what I would want to move around would be, this could be counterboards, it could be something like that, areas I need to preserve as part of that. So we can define, as we take a look, I can define the different, let me jump out of here. I can determine what is preserved geometry and what is obstacle geometry as I'm creating this. So I can say, okay, well, this one is, and I've already defined that portion. Similar to what we had before, we could put in specific structural constraints, fixed points in here, and that's what I've come along and done, and I fixed some locations. These, do not change. Those are fixed locations we have in there. And then we could put in any particular structural loads that we wanted to on that, just like I did before. And I have, in this case, I've got a couple of loads and constraints already placed on here. Gravity is part of it. I'm putting a specific force that's coming back up that's part of that. All of that is built into here, and I've already got that set up where those are fixed. In each load case, there's gravity, a fixed force, and we've got the idea. So this is really strange. I think of doing design starting like this, maybe figuring out what I can lighten from that. In the case of this bracket, I'm almost designing the opposite, And this I've seen a lot with FEA. I've seen a lot with CFD, where you wouldn't design the part, you would design the flow or something like that. That concept is here. I can specify objectives that I'm going for. Do I want to minimize mass? Do I want to maximize stiffness? What kind of safety factor am I going for? And when we look at manufacturing, I could say, you know what, are we doing additive manufacturing for this? So in this case, this would be 3D printed, and I can control for things like overhang angle or minimum thickness. So those factors are being built into this even before I say go. Now that I've got that, I'll do a pre-check, and it says, hey, look, everything you need to generate this is here. So I'll say, great. Give me a previewer. And what you'll see when I do a previewer is it's going to take a minute, and it goes through. This really tends to be a lot faster than computing you would do on your desktop, because we are leveraging cloud computing to do this. And you start to see it build this blob. And it's trying to figure out the limitations that are there and what to avoid, what to keep, how to attach all this information together so that it matches up. And this is giving us the very rough beginnings of where this is going to go. And you can see with each iteration as it goes through, it's okay, it's got to avoid this one, it's got to connect to this one, and it's got to avoid and connect. And it's beginning to walk through to generate a rough preview. It's very rough at this point of what this bracket might look like. But we're getting a sense of what that's going to be. Now that I've got that, I can generate it. That's fine. Let's stop the previewer. And I will talk about this. I'm going to do this, generate this particular one, and it's going to use my cloud credits. So cloud credits, this is something, I'll point this out again in a moment. And I've actually got two different accounts here. This one is our reseller account where I've got tons of cloud credits that I can pull from. And I actually probably will pull it from there. It takes about 25 cloud credits to run a study. You can purchase those directly from Autodesk. You can purchase them from ImagineIt. And now it's going to go through and it's going to be working on, it's got a job of generating these studies. So it's going to send it up to the cloud, and it's going to begin generating these. And what we're going to see is it's going to ultimately generate not one, but many of these as it comes through. So it's telling me that thumbnails for my outcomes, it's going to appear while it's processing. So as it goes through and processes and solves one of those, we'll begin to see those thumbnails appear, and we'll see that information. I'm just going to say OK. So it's running the study. It's going through and looking at the outcomes. It's figuring things out, such as visual similarity, how much they're going to, do I want to group that together? How do I want this to appear? And it's going to take the time to generate some of these for me. And I'm going to give it just a minute. We should see a few here fairly quickly. And then I'll go ahead and jump over and take a look at some finished studies that I have of that, and we can take a look. The concept is, with generative design, I'm not doing my final complete part and working backwards. I'm actually going the other way. I'm defining conditions, locations where things are fixed, and then pushing that to the cloud so that it generates off of that. All right, so this is taking just a little bit longer. We might come back to this one. What I want to go look at is a finished example of that. Take a look at some outcomes. So with my bracket, these are some that I worked with earlier. This will give you a sense of what we're taking a look at. So we had the original bracket. Let's see where I'll still load my outcomes. So we had my original bracket, and what we had set up was, okay, there's locations that I want to preserve. This has to be here. This has to be here. There has to be a hole in it. This has to be here. This has to be there. There has to be a hole in it. And we have to have room in the middle for something to go. So generative design is able to come up with that outcome. Here's another version that I have here. I'm going to go select this one. It's still opening up. Perfect. So I can take a look at different versions that we have of this particular bracket, see the different ways that it is created. And now this could be sent directly to additive manufacturing so that we can begin manufacturing this piece 4 here. There's a big difference between this starting shape, right? This very standard, what I would think of as, might be a casting or something, what I would typically design, and the idea of an outcome that's being generated just like this. They're going to meet the same criteria for stiffness, the weight, all of those things, but we're going to see very different design types depending on what we've created. Let's going to see if we've got any. All right, so it's still almost still creating some designs. Here we go. So you see it's queued up and it's creating all of these different generative studies for me as part of that. And as they complete, we'll be able to pull them up. So generative design takes that basic constraints, these areas, these groups, these, it'll be held here, here, and here, and it can take that and push that on up to the cloud. We can then use the power of the cloud to generate these different studies. Okay, so I'll point this out. Commonly, a way that I might approach this is I might say, well, that's great that I can do that generative design, but I'm so used to drawing, I'm so used to modeling and creating things within Inventor. And this is a really cool thing that we can do since we can leverage that desktop connector. We can take the basic shape that we have and push that up to the cloud using the desktop connector. I want to point out what I did here. This, I just came in and I did a quick save as. I took that original piece that I had. And then I went through and created some extra solid bodies in there. Literally all I did was created a sketch, projected some information, and then extruded it. And that allowed me to create, very similar to what we saw in that other design, locations to keep and a location that I want to remove. Or excuse me, to avoid, not remove. Locations to keep and a location that I want to remove. Then, when I save this, I'll go ahead and say Save As, and, excuse me, I want to save a copy as, because I want to save this out too. I've got the desktop connector installed, and that gives me a location in here called Fusion 360. So I can save this directly to Fusion 360, push this information up here. I'll just save it right to that base folder. Push that information up there, and now that is in the cloud. Oh, I got to go into a folder here. And I've done this one, so I'll just overwrite the one that I have. That's fine. Okay. That'll overwrite the one that I have. So that'll push that directly up to the cloud where I can then use Fusion to go and open that up. I'm just peeking here and see if they're if I've got anything completed yet. Nope, looks like it's still going through and processing the different ones I have. I just was hoping I had one completed. But now I just want to point out that I do have that. I forget which folder I put it in. That where I loaded that up, and I can go find that particular file and bring it into Fusion. So I can build my boundary conditions within Inventor because I'm so used to it. I've already got other parts that are going to mate to it, and then push it to Fusion so I can do that final design and final outcome that I have as part of that. So I mentioned the idea of cloud credits, and this technology, the idea of that generative design, generating those different pieces, it's really only available with the collection. You have to be on subscription. You can't get it with an education license of Fusion 360, and it does consume the cloud credits. Each user gets about 100 credits. When you just sign up for Autodesk, you get about 100 credits. You run a generative design, it's 25. Contact, you can buy them directly from Autodesk. You can buy them through Imagineit. You can purchase more cloud credits that, to add to your account. Now, the more people you have in your account, each user gets about 100. So as you have more people at your company, you can leverage those. Each person can run about 4 of these generative design studies. But the idea is we've got tools that are available to create things that would be really difficult almost any other way that we would want to set that up. And that's part of the idea of generative design, creating those lightweight components in a really clever, kind of interesting way. So Cassie, that's the general overview that I wanted to give, and I'm just jumping back because I think this thing is so cool. I'm going to jump back to the Volkswagen. And so